Okay, so we're going to be presenting Pwn 2, which is a continuation of the last meeting, or the last Pwn meeting, Pwn 1. Okay.
I'm Tyler Mercado. I'm a SIGPwny helper and I'm a statistics and computer science major. A fun fact about me is that I like game hacking and specifically like SMM module based cheats, like just directly modifying your BIOS at that point to modify memory in games.
I'm Jake. I'm a SIGPwny admin. I'm majoring in CS, math, and you should join the embedded team. We do cool stuff if you're interested in embedded systems. And this is the flag. We'll show it again at the end so you can get it. It's just 8% Ps. Then the image there is kind of an interesting example of something we're going to be talking about today, which is format string vulnerabilities, where this is, I guess, just bricking iOS's Wi-Fi. So here's like a review of like some of the stuff we're talking about in Pwn 1. So buffers and variables are stored on the stack, which is fixed size, continuous. It's continuous in memory. Unsafe functions can write more data than the buffer can store, which leads to buffer overflow vulnerabilities. And we can control the program flow by overriding a local stack variable and going like further down the stack into modifying the return address. I realize this is what I presented last year, but you're supposed to present this, right? So sorry.
So shellcode is a term for bytes of executable instructions that we plan to run. You can write your own or Google existing exploits. If you attended like the x86-64 assembly meeting, that'd be like really helpful here. And so there's like a whole database of like different exploits that you can run, like just reading and writing to files or just opening up a shell. Let me use this. Oh, up button. So, for instance, if we have our shellcode in memory, we would want to execute that. And in assembly, you can jump to that section in memory that contains your shellcode. And the most common way of doing this is overwriting your return address on the stack. But the issue, in order to actually get to our shellcode on the stack, there's like certain mitigations in place where like addresses of in this on the stack are like randomized. So to jump to our actual shellcode on the stack, we need like some address that's already on the stack, and that's where we get to stack pointer leaks. So there are certain like mitigations in place. For instance, if you could just write your shellcode to the stack and execute it, then you'd be done. You could just like open up a shell if you could just execute on the stack, but modern code or like modern compilers will make it so your stack is only readable and writable. And ret2 shellcode will only work if you have access to writing in a memory region and executing in the specific memory region where you want to have like your shellcode to be. So the solution is that memory should be writable and executable. And aside, when might we want both? So like, you want both to like be able to write shellcode and actually execute.
Or like, what is an example of maybe a legitimate use of this? If anyone has an idea for when you might have write and execute on some memory region. Okay. Anyone? No. All right. So the idea here is that just-in-time compilation. There's ways to get around this, but it's in some sense it is doing these things, right? Because it's compiling to write the code at runtime and also execute it. But it doesn't necessarily mean the region has to have those at the same time, but
There's things also mitigations called virtual memory protections. You'll learn about this in CS233, where you'll learn like MIPS and stuff like that, or ECE 391. And so for our purposes, you really only have to understand that you have the program data, your program globals, your stack, and your heap. And these are all like allocated specific sections in memory. Like, so this is like not on your physical RAM. Your RAM is split into specific pages, and then these sections here are have like different or different flags where you can set it to like it's about like 4 kilobytes per section, but you can set like specific sections to be read and writable or writable and executable or read and executable. And is there ever like a point in memory where you would just want only write only permissions? Does anyone know? Like when would that be useful? Yeah, I thought the same thing.
Yeah, the answer is cannot have that.
It's kind of useless to just have write only memory because you're just never going to use it. So another mitigation in place, because I think in PWN we learned about buffer overflows. So if you see here, like right before we go back to return, we have this thing called a stack canary before our return address. So if we're arbitrary, or if we're like writing to memory, like past that or past your specific like buffer, you'll overwrite. If you're like trying to overwrite your return address, you'll actually end up writing to your stack canary. And if like this is like just some randomly generated value that's like generated at runtime, so you don't know what this is. Well, like generally you won't know what your stack canary is. So if you write to it, your program will check if the stack canary is like the same as what it expects, and if it's not, then it'll just crash. And so there's ways to get around this. So we can actually leak the stack canary, and if we can preserve that while writing with our buffer overflow, then we can actually still overwrite our return address if like we preserve our stack canary. Another really common mitigation, I think most challenges will have this. For instance, there's like things like kernel privilege escalation challenges where they won't actually randomize kernel space memory, but generally in most like binary exploitation challenges in PWN, you'll have ASLR, which is address space layout randomization, and position independent executable. So PIE is like a flag of an executable that states that ASLR can work on that executable. So like it's designed to work with randomized addresses. Um, so without PIE, our code is loaded into a fixed address. Traditionally, the base address of that is 0x400000. So without ASLR, we could theoretically just, for instance, if like glibc was set at a specific address, we could just we can disassemble glibc, find the address of, for instance, system, and then we can just directly write that into our return address and then call system with bin.sh because that address will also not be randomized, and it would be really easy to just exploit that. So with address ASLR, those addresses are randomized. So you actually have to calculate that at runtime. And what this will do is that actually sometimes you'll have to have more than one vulnerability in your code to actually like achieve like arbitrary code execution. So what this is that, for instance, maybe your program is like normally located at this address. That's like the base address of your program. But with ASLR, it just becomes randomized. So it could be something completely different. And all of your addresses in your program are calculated at an offset from this address. So if we know that, so if we can find this address, this is our base address. If we can find this, then we know, like through disassembling our binaries, where like functions are in memory. Because we just add like the offset from like our disassembler to this value, and then we have access to all of those functions. We know where they are. So exploit primitives were you presenting exploit primitives?
All right. Yeah, I can talk about exploit primitives. So this is sort of how we build an exploit out of parts, and this is sort of a taxonomy of some of like the memory primitives that you'll be interested in. So read, there's an arbitrary read, which means you can read a value from anywhere. And there's also an uncontrolled read, which means read starting from some address and maybe the bound isn't correctly controlled, so you can read further. Write primitive, you could have arbitrary. So this is write what, where. It's a very powerful condition where you can write any value anywhere. And there's uncontrolled, which means there's one kind of uncontrolled where you can write something to anywhere, and then, or you can write anything to somewhere in particular. And then a leak is usually done with a read, but not always. So it's useful when your addresses are randomized and you need to, get the offset in order to proceed with your exploit. So in PWN1, we had uncontrolled write, which was with a buffer overflow. But now we're going to give you binaries with these mitigations that we've been talking about. So we can use arbitrary reads in order to leak information to jump to a randomized location of memory. So this is the ASLR. Keep the canary intact so the program doesn't crash when you try to override the return address. And then use existing executable code wherever allowed, because again, your stacked memory is not executable. So that won't work for writing shellcode or something. So to bypass some of these mitigations, the no execute mitigation, we can return to existing executable memory. So this might be code in the standard library known as libc or the program itself. And to bypass the stack canary, we need to somehow keep it intact, which means we need to leak the stack memory to learn of the canary's value so that when we go to override the return address, right before that, we can place the correct value of the stack canary. Then to bypass ASLR, we would need to leak a pointer to some program or stack memory so that we can infer the randomized offset that ASLR introduced. So this is our dangerous function today. This is a formatted print function, which is pretty convenient because string manipulation is sort of annoying in C, but this makes it not so bad. So the idea is that you can specify kind of like something like a template string on the first argument, and then the next arguments are what get filled into the template. So the first one, it's like, hello, Kevin is the first argument, so that gets filled in. Next one, you can also specify a number with %d. That will be filled in with the number. And then you can also have several of these, which is what the third example is showing. So Kevin, my favorite number is 1237. And %s and %d are examples of format specifiers, which is telling the printf function to read an argument and interpret it as a particular data type. So for instance, %s is string, %d is a decimal integer, and %p is reading as a pointer. So here's maybe a few ways this might go wrong. If we put the wrong specifier for an argument, it's going to misinterpret the argument. In this case, we're just printing the address of this string as an integer. So maybe that's not the worst thing ever. But what if we have maybe more specifiers, like format specifiers, than there are arguments? It'll still print something, but it's undefined behavior. So there are too few arguments actually provided, but printf, doesn't really, there's not like an argument counter or something in like a register. So it doesn't really know how many arguments there really were. It'll just go to the right place to read those arguments. And then it will treat them as if you'd actually called it with those arguments. And then kind of where this gets really bad is if you just call printf with a string that the user has control over. The user can, they could just put in some normal string. So it says Kevin, it'll print Kevin. But if they put %s, now that's a format specifier, and there's not the corresponding argument to fill that format specifier. And this is sort of how the format specifiers are specified, like in bold precision. Some of these you probably don't care about that much, like for floating point decimal precision, like maybe you don't care, but this is like the detailed way of how these are specified. Copilot. All right, cool. Okay, so primitive for stack read. So like %p, where we're saying it prints a pointer, right? It prints out in hex. This is kind of an example of how this would be used correctly. But what happens if we just call it with %p, no argument? What's going to happen next, right? So to review, this is how the calling convention works on x86-64. Your first argument goes to RDI, second RSI. And then as we keep adding more arguments, these get added to the registers. So yeah, the first few arguments get put onto the registers. But then after that, we're going to run out of registers because there's only a certain number of registers. So the arguments start spilling over into the stack. And what this means is if we have a format string with a bunch of these specifiers, it's going to read the first few registers for the first few format specifiers. But then afterwards, these are going to start reading down the stack and start reading the stack data. So the primitive for stack read is basically we just put a bunch of these. And eventually we'll print a few registers because that's what the calling convention specifies for the first few arguments. But then after that, we start printing out stack memory, 8 bytes at a time. So we can start to figure out what data is what we want. And like, for example, if there's a string on the stack, it gets printed out like this. This is a little endian. So this first byte is actually corresponding to the end here. So for these 4 bytes, it would kind of go sort of in reverse order. These are the hexadecimal representations of these ASCII characters. So 73 corresponding to lowercase s. And yeah, this is a reminder that x86-64 is little endian, so %p will interpret the data as little endian.
So I saw you had a question up there.
Okay.
So printf is what's commonly known as like a variadic function. And so right here, you can see that it's like starting to read just from the registers, like RSI up to like, it's like R9 or something. And so I think there's like a set amount of registers it typically reads from, and then it starts going to stack memory. So like you can just like count like how many like %Ps you put, like how many like pointers are you reading until you get to like the stack. And you can actually confirm when you're at the stack because it will have like some like really big address number rather than like some like the registers might contain like the number 6 for instance, but then you'll know that you're at like stack memory because like you'll get like a number like 0x7FFFF03 or something, like some really big address. And later I'll like show you how you can actually confirm like that's like a stack address by like seeing like through debugging.
Yeah, and I guess, yeah, this is the calling convention. So the first 6 arguments of a function are put onto the stack. So that would be the first 5 format specifiers. And then after that, the 6th one would be reading off of the stack. Yeah, so now we can talk about how we can start to do arbitrary read, not just like, reading a little bit more. There's a number that you can put here that will specify which position of the arguments you're looking at. So this here, this 3 is going to look at the 3rd argument here. So we can kind of put an arbitrary number in there to go further down the stack without, just having %p, like, and so on. So this is how we can do arbitrary read. Again, like for n, if we have the correct n, it will actually go down the stack until we hit this string, this character array, and then we will just print out the value that is stored in name. So the key idea is that format specifiers can read from the stack, and the name is on the stack. So that means that if we keep reading far enough down the stack, we'll eventually hit that stack variable. And also what's really important is that the format specifiers can reference our input because our input is also on the stack. So if name is like this for the correct n, it will give us back our input. Or it'll give us a string, it'll print a string that is part of our input. So this can be combined with putting a memory address into here. And then if we point %s to reading this address, it will actually read the memory at that address. So this is how we can do a fully arbitrary read where we specify the address in our input string, and then it will read that value. So I guess something that we need to keep in mind though for this, why they're underscores, is because pointers are, or because when we're reading these stack variables, we're going up 8 bytes at a time. So it needs to be correctly aligned so that when we actually specify this format string specifier, it will read exactly the address and not like start like halfway through or something. And the testing strategy is develop with P instead of S to verify that the correct address that you're looking for gets printed, rather than like getting confused because probably SIGFault when if it reads an invalid address. And then you can switch to %S once you have verified that the correct pointer value is in there. Arbitrary write. So for some reason, printf is interesting in that it will not just write memory, it will not just read your arguments, it will also sometimes write to your arguments. %n will write the number of bytes that have been printed so far to the argument that you provide it. So for instance, %n at the start, and you give it the memory address for like your int that you're storing this counter in, it will just give 0 because you haven't printed anything yet. Then if you do 4 characters, it will set number to 4. Then if we do this, we will just print 500 characters because this is padding P to have 500 characters. So now we're starting to get something that looks like arbitrary write because we can specify the value here and it will write that to this number. Yeah, so in this case, it'll print like it'll point like the printer, sorry, it'll print the pointer and it will pad it to be a total of 500. So yeah, the testing strategy again is to use the P specifier, so we verify that we're getting the correct address, and then we'll actually switch it to %n to actually write it to that correct address, and then by default it'll write 4 bytes, but you can actually change this if you need to write less than 4 bytes to the whatever target address. So HN will write 2 bytes. HHN, which is like half of n, will write 4, or will write 1 because that's a quarter of 4.
And so libc is a program that is loaded at the same time as your program, which holds like the standard library. So like when you call functions, for instance, like printf or like puts or gets, that's a part of like the standard like C or the standard C library. And so if we get, so like libc contains like a lot of really powerful functions like system, which at that point you just have like a shell on the actual like system you're trying to attack. So if we can get a leak to libc to like, because libc isn't always like put in the same part of memory due to ASLR, if we have to get like a leak to libc. So for instance, like maybe we're using puts inside of like the address to puts is stored inside of the stack. We can abuse printf to actually like read that address, and then because we can usually disassemble libc, we can find the address of puts inside of libc, and then we can calculate its offset from like the base address of libc, and then from there we can like access any arbitrary function inside of libc. Another thing is the global offset table. And so this is like standard with like ELF binaries where you'll have like just a table full of like addresses that are like standard for like libc functions. And this is actually like in writable memory. So for instance, like puts is stored inside of the GOT. And if we can get our stack leak and like find, for instance, like the global offset table offset to puts, we can actually overwrite that to like our address that we know, like to like system, and then we can call it with bin sh. Because like for instance, libc contains a string /bin/sh, and that's like pretty standard. And if we can call system with bin sh, we just have a full reverse shell into that system. Also another way of like sort of verifying that you have like the correct stack address is actually just using GDB and like finding like what's actually stored at this address. And a lot of CTF challenges, they'll give you like the libc file and like the binary loader. So you can actually like test it locally to see if like your exploit is working. And using GDB you can like just verify that you're reading like the correct like function off the stack that you're trying to target.
Yeah, there's a tool known as OneGadget that is going to search for some, well, a gadget that will give you, they'll basically pop a shell. It'll do the execv syscall with bin sh. So yeah, this is basically, if you set your return address to this, it will open a shell given that some constraints are met on the registers. And there are generally several positions in libc that might be useful for this. So this is, I guess, an example of us running one gadget on some version of libc. And with certain preconditions that have to be met, it will execute binsh and pop a shell. So this is kind of like a very simple way to have like a target for what you're trying to set your return address to. So next meetings are crypto 2. So you'll learn about more security related stuff with cryptography, which cryptography is really security. But in particular, we're going to be talking about RSA. And then next Sunday, we're going to be talking about Python jails. So you can learn how to escape Python sandboxes, which, I mean, you're in school right now. You've probably seen some sandboxes before. So